Olá a todos, boa tarde. O meu nome é João Dias, trabalho na Ciência Viva, na ESO Portugal, programa educativo em parceria com a Agência Espacial Europeia. É um prazer estar aqui com vocês. Vamos assistir a uma conferência de imprensa do ESO e do EHT. Atenção que eu disse ESO e não ESA. ESA que é Observatórios Europeus do Sul e a ESA, a Agência Espacial Europeia, para a qual nós, ESO Portugal, somos um polo educativo que trabalha na Ciência Viva. E EHT é o projeto do Event Horizon Telescope, que tem várias cadeias de radiotelescópios associadas, trabalhando em rede, em interferometria, conseguem reproduzir imagens, ou melhor, uma imagem só, através de várias observações independentes, com grande qualidade. E o que é que eles observaram? Em 2019, vocês estão lembrados, em abril de 2019, se não me engano, a primeira campanha permitiu obter a primeira fotografia, não de um buraco negro, mas da sombra do buraco negro. Já lá vamos falar disso mais tarde, ou falarão eles melhor ainda. E permitiu descobrir ou confirmar as teorias de Einstein, nomeadamente a sua teoria da relatividade geral. Foi observada então uma galáxia chamada M87, o catálogo de Messias 87, e o buraco negro fica no seu interior, que tem qualquer coisa como 6,5 milhões de massas solares, imagina, o monstro que é. E o segundo objetivo para esta segunda campanha, sendo que o primeiro era dar continuidade a essas observações, é de observar o centro da nossa Via Láctea. E o tempo que sobrar foi para observar objetos, corpos celestes que tivessem no seu interior buracos negros supermassivos, que é uma coisa que ainda vai ser desenvolvida certamente mais adiante. E também falaremos com o nosso convidado, que já lá vamos ver também quem é. E esses objetos estelares, objetos celestes, perdão, são essencialmente núcleos galácticos ativos. Falamos de galáxias bastante distantes, com buracos negros supermassivos no seu interior, que podem levar, por exemplo, os quasares. O quasar é, já agora, a abreviatura de Quasi-Stellar Object. É um objeto quase estelar, parece ter o brilho de uma estrela no céu, mas é uma fonte de luz imensa, altas energias, que se situa muito longe de nós, portanto, tem um desvio para o vermelho extremamente acentuado, e por essa razão o seu próprio espectro de emissão aparece completamente desfasado. Bem, agora já estou a falar de coisas um bocadinho mais profundas na área da física, vou deixar isso para realmente entender, e vou então falar aqui muito rapidamente do que nos espera nesta conferência. São várias que estão a decorrer ao mesmo tempo. Esta é do ESO, é na Europa, em Garching, na Alemanha, e temos outra que vai decorrer na América do Sul, do ALMA, e muitas outras. Todas elas vão decorrer ao mesmo tempo, comunicar os resultados inéditos que eles anunciaram. Vamos ver quais são, tem a ver com a nossa galáxia, com a Via Láctea, ao que parece. Segue-se depois uma sessão de perguntas e respostas só para os jornalistas. Depois teremos uma entrevista com o nosso convidado e, por fim, se conseguirmos também acompanhar o Q&A, as perguntas e respostas do público do mundo. E já agora, ainda temos aqui alguns segundos, estou aqui a ver o tempo para começar a conferência, só dizer isto. Este projeto assenta, não é um telescópio só, são várias cadeias de telescópios, ou melhor, de vários radiotelescópios ligados todos em linha, em várias partes do mundo, porque todos juntos funcionam como se fosse um só, como se fosse um diâmetro imenso da antena, e quanto maior for esse diâmetro da antena de um telescópio, melhor são as qualidades das suas observações. E para observar uma coisa tão distante e tão potente quanto um buraco negro, que emite raios-x, raios-gama, tinha que ser mesmo desta forma. Portanto, a seguir segue-se a entrevista ao Hugo Messias, poderão fazer perguntas se quiserem. Entretanto, agora, em breve, vou-vos deixar. Vai começar a conferência em Garching, vai uma começar no ALMA, onde o Hugo Messias vai estar a participar. Há várias a acontecer ao mesmo tempo e esperamos que acabem também ao mesmo tempo para podermos falar com ele no final. Então, boa sessão e até já. Obrigado.
Good afternoon, and thank you for joining us here in Garching, Germany, at the headquarters of the European Southern Observatory, or ESO for short. Thank you to everyone watching us online as well. Today, we'll be hearing from the Event Horizon Telescope collaboration about their newest results, so please do switch off your mobile phones to hear them. I'm Bárbara Ferreira, I'm the media manager at ESO, and since we don't have much time until the main results go live in multiple press conferences around the world, I'll quickly present the format of today's event. First, we will hear from ESO's Director General, Xavier Barcons, and then from lead Event Horizon collaboration scientists about the main research. We'll then open the floor for questions from journalists only, be it those here in the room or those watching remotely. I will now hand over to Xavier to open the proceedings.
Hello, thank you. Good afternoon. Warm welcome to ESO to everyone. It's a really great pleasure to be here today, hosting the members of the Event Horizon Telescope collaboration as they prepare to announce their most anticipated results following the unveiling of the first image of a black hole back in 2019. Today, we're going to see something really new, exciting, extraordinary at the center of our galaxy for the first time. We've been so close to it many times before. ESO facilities like the Very Large Telescope and the VLT interferometer, in addition to the Keck telescopes in the US, have observed stars moving around the compact invisible object at the heart of the Milky Way. And for sure, the ESO Extremely Large Telescope will continue doing this in the future towards the end of the decade. The movements of these stars have been tracked for decades using specially crafted instrumentations. These measurements offer the best and very solid evidence so far that these stars can only be orbiting a supermassive black hole. Reinhard Genzel, who is with us today, thank you very much for joining us, was awarded the Nobel Prize back in 2020 together with Andrea Ghez in the US for exactly this discovery. But we are yet to see direct visual evidence of this compact object, which astronomers call Sagittarius A star. This extraordinary result would not have been possible to achieve by one single facility or even by the national astronomical community of a single country. It took 8 radio observatories around the world, and that network has already expanded to 11 today. Many built, funded, operated, and supported through international organizations across many countries around the world. Among those, ALMA and APEX in the Atacama Desert of Chile, which are co-owned and co-operated by ESO, as well as European facilities like the IRAM 30-meter telescope in Pico Veleta and the NOEMA array in the French Alps. It also involved an international team of about 300 scientists, plus many others supporting them, like engineers and many more people. And altogether, it shows what we can achieve when we cooperate, when we work together. This is very important to remember in the times that we are living in, where the world is not running in that direction, unfortunately. ESO was founded 60 years ago, precisely to foster international cooperation in astronomy, so we can jointly tackle the biggest open questions in the universe. And indeed, a key motivation for ESO to put its telescopes in the Southern Hemisphere was to enable science to be done around the center of the Milky Way. So this is why it's such a big pleasure today to be here hosting this event. Together with me, I have 2 of the leading figures of the collaboration, the EHT project director, Hope van Lankevelde, chief scientist at JIVE and also professor at Leiden University, and the founding chair of the EHT board, Anton Zensus, director of the Max Planck Institute for Radio Astronomy in Bonn. Anton will later be telling us about the European facilities involved in the EHT, and now Hope will now present the main result. So over to you, Hope. Thank you very much.
Thank you, Xavier. When I entered the field of radio astronomy as a student, I was told about this enigma, this mysterious radio source, Sede star, at the heart of our galaxy. I observed it at long wavelengths, and there it appears to be blurred. It's very exciting here today to show you today this best ever image of that enigma Sede star. I will do that with my team, or with the team, but I would first like to remind you that the team is much bigger than fits in this audience. In fact, it's bigger than fits in the auditoria around the world where this press event is taking place simultaneously. We are over 300 people on these papers, and only very few of us get to be staged here today to share the result with you. To share the result, we will be flying into the heart of the galaxy, some 27,000 light years away from us. We will do that in 45 seconds. That's a violation of Einstein right away, but maybe that's probably the only violation of Einstein. So we start out from the plains of Chile, where the ALMA telescope is located, and we're going to zoom in to Sagittarius, the Archer, which is high in the sky above the northern Chile. And we will go and zoom in first in the optical, but we have to switch to the infrared because there we can penetrate all the way into the galaxy. We leave tens of millions of stars behind, and we get to the place where stars are in orbit around a dark spot. And when we switch then to our radio eyes and we use a network of telescopes to resolve further and further, I can present to you the image of Sede star, the black hole at the galactic center. I will now introduce my team in reverse order here on stage, because that went really fast. Christian Fromm is from Frankfurt and Würzburg University. Maria Felicia de Laurentiis is from the University of Napoli and the Italian Nuclear Research Facility. José Luis Gomez is from the Instituto de Astrofísica de Andalucía in Granada. Thomas Kriegbaum is from the MPI in Bonn, but to lead on explaining what we have seen and what it all means, Sarah Issaoun is from Harvard and Smithsonian and Radboud University.
Thank you, Hub. Ooh. This is the first image of the supermassive black hole at the heart of our Milky Way galaxy, Sagittarius A star. For decades, we have known about a compact object that is at the heart of our galaxy that is 4 million times more massive than our sun. Today, right this moment, we have direct evidence that this object is a black hole. The black hole resides inside the dark region at the center of this image, where its gravitational pull is so strong that light cannot escape, and only darkness remains. We call this region the shadow of the black hole. This region is surrounded by very hot gas swirling around the black hole. This gas emits radio waves we observe with the Event Horizon Telescope. These radio waves create the glow we observe around the shadow of the black hole. From our image, we measure the size of the shadow of Sagittarius A star to be 52 micro-arcseconds on the sky. This is about the size of a donut on the surface of the moon as seen from Earth. In reality, Sagittarius A star is about as big as the orbit of Mercury around the sun, but at a distance of 27,000 light years. Because the size of a black hole shadow is proportional to its mass, our image tells us that the mass of Sagittarius A star is 4 million times greater than that of our sun. It is really incredible that this prediction from Einstein's theory of general relativity matches the mass measured by the Nobel Prize-winning studies of stellar orbits in our galactic center. Today's image might look familiar to some of you. We were all amazed that the image of Sagittarius A star looked so similar to that of the famous black hole in the M87 galaxy, an image our team revealed back in 2019. However, Sagittarius A star is over 1,000 times less massive than M87 star. If Sagittarius A star were the size of this donut right here, tiny, M87 star would be the size of the Allianz Arena, the Munich football stadium just a few kilometers from where we are today. On top of that, Sagittarius A star consumes gas at a much slower rate than M87 star. And these two black holes also reside in completely different environments. Sagittarius A star resides at the center of our small spiral galaxy, whereas M87 star resides at the center of a giant elliptical galaxy and ejects a powerful jet of plasma. Despite all these differences, the images of these two black holes look very similar. Why is that? This similarity reveals to us a key aspect of black holes. No matter their size or the environment they live in, once you arrive at the edge of a black hole, gravity takes over. The journey to the edge of Sagittarius A star spanned decades of technical and scientific developments, and I will pass it on to my colleague Thomas to tell you all about our adventure. Thank you very much.
Thank you, Sarah. Imaging a distant black hole would not have been possible without a big telescope of very high magnifying power, or angular resolution, as we astronomers call it. To achieve this, astronomers combine radio telescopes located around the globe to create a super telescope which has the size of the Earth. This technique is called very long baseline interferometry, or short VLBI. While the Earth is rotating, all telescopes observe the same astronomical objects for several hours. At each telescope, the data are recorded on hard disks and are accurately time-tagged by precise atomic clocks. After observations, the data are shipped to processing centers where they are combined in supercomputers. These supercomputers are called correlators. After a number of quite complex data analysis steps, this results in the high-resolution image of the radio source. It took more than 25 years to optimize this observing technique and make it work also in the short wavelengths 1 millimeter band, where the angular resolution is highest. It required the development of quite complex and very technically challenging techniques and data acquisitions so that the wider observing bandwidth could be used to achieve this better sensitivity. This sensitivity is really needed for the accurate imaging of the faint event horizon scale structures which we are now seeing in Sagittarius A star. A decade of pilot studies paved the way in Europe and in the US for the formation of the Event Horizon Telescope. The EHT is a VLBI network of telescopes which combines radio waves at 1.3 millimeter wavelengths. This wavelength is short enough to see the swirling matter around the black hole. During the Sagittarius observations in 2017, the EHT combined 8 telescopes. Since then, the network has already grown to 11 nowadays. The radio telescopes of the EHT are located at particularly high sites to minimize the influence of the atmosphere and the water vapor on the observations. Examples are the ALMA and APEX telescope in the dry Atacama Desert in Chile, the IRAM 30-meter telescope in the Sierra Nevada close to Granada in Spain, and the NUEMA interferometer in the French Alps. With this, the EHT achieves an angular resolution which is sufficient for the imaging of such distant black holes, and also sufficient for the matter surrounding these black holes. To give you an idea, the EHT can see 3 million times sharper than the human eye. So when you are sitting in a Munich beer garden, for example, one could see the bubbles in a glass of beer in New York. Sagittarius A star was observed by the EHT in 5 observing runs during April 5 to 11 in 2017. These telescopes also included, for example, special places like the South Pole. The telescopes recorded a total of 6,000 terabytes of data, which were then shipped to the 2 correlator centers, one being in Max Planck Institute for Radio Astronomy in Bonn, and the other one at MIT Haystack in Massachusetts, close to Boston, in the US. The amount of processed data is really very, very huge. It would basically, if you would print this data on A4 paper, the paper stack would reach the moon. Of course, we are not going to waste such much paper. After correlation, the calibration and sophisticated data analysis took several years and required the development of many, many new tools by the members of the EHT collaboration. In this development, we also honor the substantial contribution of very many young scientists who just start their careers now. For the details of this amazing imaging process, I would like to refer to my colleague and the next speaker, José Luis.
Thank you, Thomas. Thank you very much. Yes, as my colleague Thomas mentioned, the EHT is like a giant Earth-sized telescope, but it doesn't work like a regular telescope. Instead, the radio telescopes of the EHT work in pairs, with each pair collecting the information required to obtain an image. As the Earth rotates, the separation and orientation between telescopes changes, providing this extra data that we need. With the 8 radio telescopes of the EHT, we have enough information to obtain an image, making the EHT the only existing instrument humanity has to image supermassive black holes. Imaging Sade was, however, significantly more challenging than M87. Oh my God, it was really a lot harder. Our line of sight to the galactic center is obscured by matter, which scatters radio waves coming from the region around the black hole. But most importantly, as shown in these computer animations, the gas in these 2 black holes moves at the same speed, nearly as fast as the speed of light. But Sade star is over 1,000 times smaller than M87. This means that the time that the gas takes to orbit Sade is only just a few minutes, while it takes days to weeks to orbit the larger M87. This means that the gas around Sade was actually changing while we were observing it. It was like trying to take a clear picture of a running child at night. So you would imagine how difficult and how crazy it drove us for many years. So we EHT scientists have developed sophisticated new tools to account for this rapid movement of gas around Sade star. Tens of millions of images of synthetic data created to best resemble that of Sade star have been produced in supercomputers around the world to refine all algorithms, like searching for the best lens and filter to get the sharpest ever image in your camera. The EHT collaboration has produced thousands of images of Sade star using classical methods and EHT tailored new algorithms for imaging interferometric data. As shown in these images, each one of these images is slightly different, but by averaging these images together, we are able to emphasize the common features, finally revealing the giant larkin at the center of our galaxy for the first time. But it is important to note that not all images look alike. We found that we can cluster these images into 4 different categories. The vast majority of them are contained in 3 clusters with only ring images that only has some changes in the brightness distribution around the ring, and only just a minor cluster with images that doesn't look quite like ring images. Through literally years of exhaustive tests, we are now confident to have captured the first image of the black hole in our galactic center. Sede star now holds the record previously set by M87 of the most thoroughly vetted interferometric image that has ever been made. Our detailed analysis of the images, as well as exhaustive modeling of the interferometric data, has revealed that all share exactly the same ring size, precisely measured to be 52 microarcseconds, in perfect agreement with the size predicted by prior observations and theory. Of course, we are thrilled today to show the first image of the black hole in our galactic center. This, together with the previously release of M87 image, fulfills the initial visionary goal of the EHT. But this actually only marks the beginning of an amazing area in the study of black holes. The ongoing expansion of the EHT and the significant technological upgrades will allow scientists of the EHT to release even more amazing images and, of course, movies of black holes in the future. And now, to learn what this image tells us about the black hole itself, I pass it on to my colleague, Christian. Thank you.
Thank you, Jose. To interpret the image and to learn more about black holes, we perform detailed models how the gas and the light behaves in the direct vicinity of black holes. Our models have 4 ingredients: the black hole, magnetic fields, gas circulating the black hole, and the light emitted by the gas, which is finally collected by the telescopes of the EHT. Astrophysical black holes can be fully described by their mass and their rotation. Black holes can spin either in the same direction as the gas or in the opposite direction. For the model or for the image and the source in the galactic center, we know the mass estimate very good from stars orbiting it. However, the spin of the black hole in the galactic center is rather unknown. In our models, we let mass and matter fall towards the black hole, and this matter forms a disk around it. The gas in the disk is circulating the black hole and heats up. While the gas is heating up, it starts glowing. So thus, in the EHT image, we see the glow of the infalling and outfalling material. Similar to the black hole spin, we don't know exactly what is the orientation of the black hole towards the Earth. And changes in the orientation lead to different image structure and different positions of the bright spot around the ring. Therefore, our modeling needs to cover a large range of possible spins and inclinations. Therefore, we built the largest and most detailed image library for black holes ever. For this purpose, we use supercomputers around the globe, spending billions of CPU hours creating petabytes of data. Finally, we have obtained millions of black hole images, and we compared them not only to the EHT data, but also to historical and complementary data. Our best bet model, which is playing now, shows a lot of fine details. You can see these fine arcs going around the black hole. However, when we consider the resolution of the Event Horizon Telescope, as my colleagues explained, these fine features are blurred out. And you will see this soon. This will switch on to the blurred image. So now you see the transition to the blurring. Now the fine features are gone. This is the resolution of the Event Horizon Telescope. What we found is that the black hole in the galactic center is rotating, and it's seen face on. The implications of our modeling with respect to theory of gravities will be explained by my colleague Maria Felicia. Thank you.
Thank you, Christian. As our nearest supermassive black hole, such star can be studied in ways that are not possible for other sources, making it a unique laboratory for exploring the astrophysics of black hole and testing prediction of Einstein general relativity. We relaxed the assumption that such a star supermassive black hole is described by Einstein theory and quantify possible deviation. Our finding from this new measurement of such a star provide further evidence that astrophysical supermassive black holes, independent of their mass, are described by solution of Einstein theory. For such a star, as we found for M87, the inferred size of the black hole shadow is consistent with the prediction of general relativity within the 10%. This consistency is in spite of the fact that such a star and M87 are feeding on matter at dramatically different rates, with such a star accreting 1 million times less matter. So our conclusion indicate that Einstein theory is still holding strong. And in addition of what was observed for M87, now we have the most compelling evidence to date that the supermassive compact object at the center of our galaxy is a black hole, and that it is in all likelihood described by Einstein theory. We know black hole, and in particular the vicinity of the event horizon, are becoming an observational test bed for gravitational physics. This environment offers us the unique opportunity to determine where and how Einstein theory breaks down. And if it does, of course, will transform our understanding of gravity and the property of space and time. We know very well that the idea of testing Einstein theory using our galactic center black hole is not new. But the result we have shared today represent an important step forward. So I'm delighted to be able to say that we have finally imaged the supermassive black hole at the heart of our galaxy. These measurements have opened a new window onto studying black hole and their role, their central role in our universe. The years ahead, of course, will transform our understanding of black hole and the fundamental nature of gravity. So stay tuned, because the best is yet to come. Now, I will hand over to my colleague Anton, who will give the closing remark. Thank you.
Good afternoon. This is it. This is it is a huge moment for everyone in the Event Horizon Telescope collaboration. It's the next level. And I'm proud of everyone, of our entire worldwide team. They have worked so hard for this latest breakthrough. You are the first to see our image of the black hole in the center of our galaxy, as close as it gets. Imagine this. We have combined the world's greatest radio telescopes into one Earth-sized camera. To be honest, after doing this for 40 years, I'm still astonished each time we pull this off. Let's shine a spotlight on the European facilities within the EHT, and we begin with the Armor Observatory. The Atacama Large Millimeter Array at 5,000 meters altitude in the Chilean desert. This was our game changer. Its sensitivity, because of its huge collecting area, was the difference in measuring the weakest signals. And the 30-meter antenna in Spain of IRAM, this has been our flagship for over 2 decades. It is essential for making the sharpest image. The APEX, the Atacama Pathfinder experiment in Chile, near Alma, is invaluable for precisely calibrating our signals. And the NOEMA, the Northern Extended Millimeter Array in the French Alps, with this huge collecting area and super sensitive receivers, has given a further boost to the EHT. And a supercomputer, our correlator, is a hub for the processing of the enormous data sets that are required to then extract our images. These facilities, which include the 3 largest antennas within the EHT and the support from our funders, and yes, that's us, the taxpayers, are a sustainable foundation for the continued success of the EHT. And we acknowledge the support of the national funding agencies, of the European Research Council, and of the Commission. Now that said, in its DNA and by our design, the EHT is a truly global enterprise. Well over 300 scientists from over 20 countries, and add to that telescope designers, builders, engineers, technicians, and staff. Their contributions are what the scientific collaboration depends on. In 2019, a little over a century after Albert Einstein revealed his theory of relativity, and after decades of pioneering preparatory work, we presented the first image of a supermassive black hole in the center of the galaxy M87. Nobel Prize-winning measurements by Andrea Ghez and Reinhard Genzel, and we're so happy, Reinhard, that you're with us. With their teams, they showed that there must be such a black hole in our galaxy, and we made this black hole visible for the first time, and it confirms their conclusions. So what about Einstein? Would he smile seeing all this, hundreds of scientists still not having proven him wrong? I rather think that he would be ecstatic, seeing all the experimental possibilities we have in this field today. So, mission accomplished? Yes, but there's so much more to do. We now want to go on and make movies. We want to study magnetic fields. We want to look at the jets in galaxies. And yes, we want to tackle gravitation theory again. New antennas in the EHT, like NOEMA and the African Millimeter Telescope, and ever-improving technology will enable us to do that and much more. So today we're celebrating the first image of the supermassive black hole in our galaxy. And we're talking about what it tells us and why that matters. And tomorrow we'll be back at work unraveling the mysteries of black holes in the universe. Thank you all for being with us today, and now over to your questions.
Thank you to our speakers for sharing this remarkable result with us. Before I open the floor for questions from journalists, I'd like to remind everyone that we have extensive press material, including images and videos, on ESO.org. For those of you watching online, please stay tuned, because at 4:30 we have a Q&A panel where members of the public will be able to ask questions to EHT experts. But on to questions from the media. If you are a journalist here in the room, please raise your hand. Take your mask when asking a question and speak very closely to the microphone, otherwise we cannot hear you properly on the stream. Do identify yourself, whom you are reporting for, and whom the question is for. And then we will answer questions from members of the media watching remotely, who have sent in plenty of questions already, a little later. So do we have any questions in the room from journalists or media participants? All right, if not, we can start. Oh, okay.
Hi, so I'm Teresa Paneke. I'm actually a PhD student here at ESO, and I do science communication online through social media. So thank you very much for this amazing result. I would like to ask, because we've talked a lot, or it's been said a lot, that M87 has an active black hole, whereas our black hole is maybe not accreting as much material. So when we just look at the image, they seem to be equally bright. Of course, there's the distance difference, but what exactly is the material we're seeing there? Do we have an idea about accretion rates? So what is the difference between M87 and Sag-A in that regard?
Is that for
So as you already heard, the difference is the central mass already. So the galactic center has roughly a mass of 4 million solar masses, as Professor Gensel showed us already, and M87 has billions of solar masses. The other difference that you may have noticed on my animations or from images of M87 is a powerful jet that is generated in M87. For the galactic center, we see it, as I showed you, face on. So the jet, if it's existing, is pointing towards us. It's very dilute, so we can't, at the moment, image it, and I would refer then to my colleagues to explain you a bit what we need to finally detect it. And I think these are the three major differences. It's the mass, it's the jet that's existing, and as already you said, it's a different mass accretion rate, which we have for both systems. So maybe one of my colleagues.
Yes, thank you very much, Christian. Yes. In order to obtain the image, we need to have measurements of with antennas at different separations to measure features that are very small and features that are very large. So in order to capture a possible jet inside a star and to actually capture the jet that we do know exists in M87, we need to have measurements of telescopes with short separation to see these larger scales. We lacked that information during 2017 observations, and this is why we did not see the jet in the M87, and we have not seen any jet inside J star. We do have new antennas in the observations that followed the 2017 campaign, and we do expect to see the jet in M87. It is still unclear how bright, if there is a jet inside J star, but we will be chasing it, of course.
Thank you. Yes?
Hi, thank you so much. This was very exciting for me. My name is Camila. I am with the Brazilian podcast Astronomia em Meia Hora. And I wanted to ask if the collaboration has other targets in mind already, anything like planned to observe in the future.
Well, thanks for the question. Yes, of course, we have other targets in mind. I mean, during these observing runs, we not only observed M87 Sagittarius, a star, but we observed also a number of AGN, some of which are very close by. And data analysis of this is still ongoing, but give you a warning. Since they are so distant, we will be not able to see these beautiful shadow-like images immediately. So it would require more sensitivity to really look at the very closest objects, and we are at the moment surveying the sky to find these.
Thank you. I'll take questions online now because the list is piling up. So this one is from Hans Heckenberg from New Scientist Dutch edition, and it's addressed to Sarah. What open questions that we currently have about the structure of black holes can be answered by this image and follow-up images of Sag star?
Ooh, that's a loaded question. Yes, so open questions that we can answer. I think Kristen's portion of the presentation summarized really well the major things we found out about Sag star, which is one of the unknowns is the black hole spinning, which we have the answer to that, yes it is. And what is the orientation of the black hole with respect to us, which we also did not know before. And now we're fairly confident that it is pointed more or less towards us, so face on. These properties, this knowledge of the fundamental properties of the black hole will help us study the astrophysics of the black hole in more detail later on, and also how we interpret the images. The spin and inclination have very important roles in how the image looks and how we interpret the astrophysics we can learn from it. Future observations of Sag star, of course, our current observations from 2017 also have polarization information, which we are planning to start working on, like Anton said, tomorrow. That will tell us information about magnetic fields around the black hole. And magnetic fields can tell us about how the black hole eats gas and ejects possibly a jet or outflow. So as Christian said, we still don't know if Sagittarius has a jet. Some of the models seem to hint towards that direction, but magnetic fields, learning their configuration, how they look around the ring of Sagittarius, will help us answer these questions very soon.
Thank you. Okay, I'll continue with the online questions. So we have from David Castelvecchi reporting for Nature. This is addressed to any of you. How does the measured angular size compare with the mass of 4.15 million solar masses measured by Genzel's group? Would like to take that one? Maria Felice?
It was very important to have their measurement, their astrometric measurement to us, because what we found that the size of our ring of the shadow is consistent with that mass. As Sarah said before, that the size is proportional to the mass and to the distance. For us was important this, and
okay, thank you. All right, we'll continue with the online questions. So from Sanja Venkart reporting for Wolfgang magazine in Vienna, also addressed to any of you. What are the difficulties when observing and analyzing Sagittarius A star? Maybe more for José.
Very happy to answer this. Well, many. I mean, oh my God, where do I start? I mean, the most difficult part of Sagittarius is that it's a very small black hole as compared with M87, 1,000 times smaller than this, and then we had to try to find a way in which we can overcome these extreme changes in the emission that we were observing, as we were explaining before. In order to capture an image of the black hole, we need to take a very long exposure snapshot. We are observing these sources for 8 to 10 hours. And the basic principle of the technique that we are using is that during those 10 to 8 hours, your object is not changing. And this is exactly what refuses to do Sagittarius A. So in order to that, we have created these new tools that allow us to get a little bit blurred image, adding a little bit of extra noise to compensate this variability, so that even though the image may be a little bit blurred than the image we got from M87, we do capture the main features, the most salient nature of the black hole. And this is the ring structure and all these images that we were showing before. They all share the same ring size. What we were not able to capture is what is, the brightest emission around the ring. And this is because it's changing. So we are getting these different images, all consistent with a ring, 52 microseconds, but the emission around the ring changes when we make slight changes in the way we make the images. Like we change a little bit the lens, or we change a little bit the filter, and then the image looks a little bit different. But the main image is there. And all this analysis is what took us more than 2 years, from 300 people in the collaboration, from doing the imaging, from doing the analysis, and etc.
Thank you. Okay, I don't see any hands up here, so I'll continue with the online questions. We have one from Filip Ogorzelski from TVP Nauka. This is addressed to any of you again. How much matter is being absorbed by the black hole in the center of the Milky Way? Christian?
I'm not exactly sure what he means by absorbed, but the accretion rate. Yeah. So actually, these black holes in the galactic center is secreting very, very less matter. They are basically, this black hole is basically starving. The accretion rate is extremely low, and yeah, the accretion rate is extremely low. Maybe Sarah.
Sorry for that. We calculated this for a fun EHT Twitter poll that we had. So if you were to have the same diet as Sagittarius A star scaled to your mass, you would eat 1 grain of rice every 1,000,000 years.
I would not want that diet.
No.
All right. We have a question from Antonio Pires, reporting for astronomia.com. How much did the telescopes that recently joined the HT collaboration improve the results from the previous observations in terms of resolution and sensitivity? Will we be able to increase the apparent aperture by using space telescopes in the foreseeable future? This be perhaps for Thomas?
Well, first, of course, this image which we created now has the same configuration. So the 2017 data of M87 and Sagittarius A star based on the same telescope configuration. In 2018 and following observations, we have added more telescopes. Now we have 11 telescopes, so we fill the UV plane much better. That means we can much better make a synthetic telescope, and the participation of NOEMA and also of KitPeak, for example, provided additional baseline sensitivity. We also expanded the recording rates and doubled the observing bandwidth. So all this lets us hope that in 2022, where we just observed the source again a couple of weeks ago, we will get a much better image.
Thank you. Okay, we have one from Dave Adalian, reporting for earthsky.org, and I think Christian would probably be able to answer that one. When the orientation of Sagittarius A star is said to be face on, does that mean one of the black hole poles is directed towards Earth? Do we know how fast Sagittarius A star processes, and what is the nature of the particles ejected?
Okay, so let me start first. So we found that it's face on. So this is correct, that one of the spin axes is pointing more or less towards us. The other part was about the material or the emission actually that we see. And what we model is synchrotron radiation. So you have particles, mainly electrons, gyrating magnetic fields. And while they gyrate the magnetic fields, they emit emission. And this emission is synchrotron. And this is what we actually see. And there was a third part. Could you please repeat this?
So it was the processes.
Yes. So precession, I think what you mean is spin. So what we have actually is we have some kind of best bet models. So we have not found an exact model which could explain everything. So we have best bet models and best bet regions. And there we could say that it's spinning, and it's spinning in the same direction as the gas orbiting it, but the precise number of the spin has to be obtained in upcoming observations.
Thank you. Okay, we continue with the online questions. We have one from Roberto Peixoto, reporting for Globo in Brazil. EHT observatories capture radio waves, but how do black holes emit these waves, and how can we build an image with it? Who wants to take this one?
Emission, how it produced is I already explained. That's the synchrotron radiation. So basically you accrete gas, which is electrons, they gyrate, produce the emission. And for the details of how we actually detect this and so on, I would refer to one of my colleagues working on data processing and imaging.
Is that for José, Thomas?
Yes. Then the most important part, of course, is to get an image. As we were explaining before, the EHT doesn't work like a regular telescope, so we cannot build a telescope the size of the Earth, obviously. We cannot do this. But what we do is we have these different telescopes that act like segments of this huge telescope. And then we collect the signal from all of them and create, synthesize the virtual telescope on a computer. Once we do this, and then it is possible to have basically like the Earth-size telescope and get an image like you would get an image with your mobile phone. But it is significantly more complex. You have to do. You have to make the images on supercomputers, so it's a process which is extremely complicated. But at the end, you are able to finally obtain the images of these supermassive black holes.
Okay, thank you. Another question online is from Doris Urrutia, reporting for Inverse. How did you feel when you saw this new result? What was the big reason that you felt excited enough with your finding to share it with the world. Who wants to take this one? Sarah?
So I did my PhD research on Sagittarius A star, trying to chase down this jet that is maybe real, maybe a myth. And so I was working on images of Sagittarius star at a lower frequency than EHT, so images that aren't quite at high enough frequency to be able to peer through all the gas and see the shadow. And I was trying to understand where this radio emission comes from near Sagittarius star, try to see if we could constrain the inclination of the black hole from my observations. And until today, I was also the record holder for the best image of Sagittarius star. So when working on EHT, I saw the image of the shadow. It was a really special moment because I've been working on this source for a long time through my PhD and trying to understand its properties. And there it was, staring back at me, and I felt shivers and excitement, and it was revealed as part of the whole imaging teams coming together, just like for M87. We're all on a Zoom call. I was in Japan with a few people at a Galactic Center conference, which was quite funny. It was midnight, Japan time, when we had the telecon, and we all huddled together, and the images, like Jose was leading the telecon, images were revealed from all the different teams, and everybody saw this ring of the same size. And it was such an exciting day and very memorable to finally see this object I've been working on for a long time.
How? Did you want to add?
I wanted to say one thing to Sarah. She's still the record holder.
Yeah, but now I have to share it.
Did you want to add something as well, Thomas?
Of course, this is all correct, but as a little bit older person, I realized how it all started, and I think it took now more than 30 years to get the image. So we had this idea long ago, and at that time when we started observing, the first experiments at 1 millimeter failed horribly, and we have to step back to 2 millimeter before we could do it at 1 millimeter again. And I saw that over the years, the techniques have improved so much. That's really a very, very good feeling to see now that it has worked and that we are now finally able to show that image.
It's great. I'm also very glad that you are able to share it. Okay, one more question online. It comes from Diego Garcia, reporting for Canal Sur TV. This is addressed to José because he wants you to answer in Spanish, but someone else could answer in English as well, I suppose. During this process, what have you discovered at a scientific level about Sagittarius A star that was not known before? And then there's a second part to that question. What are the biggest differences between this image and the one of the black hole in M87?
Okay, thank you very much, Diego. I probably should answer this in English for the whole community. Thanks again for your question. Yes, I think the most important thing we have learned is that first we have the visual confirmation of the black hole that was predicted a long time ago. As my colleague Christian mentioned and Maria Felicia, now we have a constraint about how fast this black hole rotates. And this is very important because we think that the rotation of the black holes provides the energy that powers this huge jet that we see like in M87. And the second part of the question was probably...
So there was one about the differences, and
yeah.
My colleagues moved the question already. So
all right, okay, it's fine.
If they can fetch it.
Sure, no, it's fine.
Okay.
Fine. Sorry, I forgot.
It's important also because we, for the second time, we were so close to the event horizon, and then we were able to test gravity at a different regime, at a different scale, and we were surprised also that general relativity is still holding, It's incredible.
So I have the question back, and it was two parts. What have you discovered about Sagittarius A star that was known before, and the differences between the images between M87?
Yes. Well, the images are surprisingly similar. I mean, as we were discussing, these two black holes they both live in completely different environments. Yet, at the end, the image is just mainly made out of the gravitational pull, as Sarah was mentioning. So, in that sense, this confirms one of the most important predictions from general relativity, which is that these are the most amazing, extravagant objects in the universe, yet the simplest.
May
They are just you know, as simple as a you know, a sphere or a circle in you know, images. Thomas.
Well, also with regard to the published results from gravity, I think there's a major difference. M87 is far away and it's much bigger, so it varies much slower. But in Sagittarius A star, we really can see the variations. I mean, we see basically bright features moving around. Although we are not able really to trace their motion exactly, we have published in our papers some models which explain this motion already. And I think the next step would be to parameterize the motion so that one can do more science out of it.
Thank you. Okay, I will continue with the online questions. We have one from Alejandra Lopez reporting for El Tiempo in Colombia. This is to any of you. So she asks, perhaps Christian, what is the orientation of the rotation of this black hole with respect to the plane of the galaxy? Do we have an answer to that?
So what I mentioned is we see it face on, and according to our models and this bad region, the rotation is in the same direction as the gas. And please, all my colleagues, correct me. It's in a counterclockwise way when you look on it. When you look at the images, it's turning counterclockwise. At least in the simulations. So the simulations, you see that it's turning in a counterclockwise way.
Okay. We have time for one more question. I'll give priority to journalists here in the room. If not, I'll continue with the online questions. And we have one from Tushnet Physics World. Do we have any ideas on why there is such mass difference between Sagittarius A star and M87 when they are both supermassive black holes? Who wants to take this one? How?
Okay. Am I on? So that's most likely to do with the evolution of the galaxies in which they are found. M87 is a very giant elliptical galaxy, and it's probably the result of merging many galaxies with many black holes together, while our galaxy has been going through much less evolution.
Okay, thank you. All right, I will stop now because we are almost at the hour, and I will thank our speakers again, and thank you all for the questions, also for those watching remotely. Journalists are now welcome to approach our panelists and other experts in the room. So EHT experts have a badge with an orange collar in it. And then there are also other experts who are not part of the EHT team, but can answer questions about the research, who have a badge with a green collar. And we have interview areas available here and up there, and you can approach myself or one of my colleagues to be guided to them. For members of the public watching remotely, do stay tuned, because we have a YouTube Q&A coming up at 4:30. And then, before that, we'll actually have a special musical performance just before this Q&A session. Do go to @ESO on Twitter to find out more about it. Thank you all very much, and thank you. Thank you.
Olá a todos novamente, boa tarde. Portanto, quem esteve a assistir teve a oportunidade de ver a grande descoberta, realmente, não mas duas fotografias já temos não de um buraco negro, mas da sombra de um buraco negro, e este não é nada mais nada menos do que o nosso, da nossa Via Láctea. Ora, entretanto, como sabem, tínhamos anunciado, e vamos manter a nossa promessa, uma entrevista com o Hugo Messias, astrofísico, que está a operar o ALMA, o Atacama Large Millimeter Array, no Chile. Como ao mesmo tempo que decorreu esta conferência de imprensa do ESO, também decorreu no ALMA, portanto é uma por cada continente, digamos, até por facilidade de transmissão. Nós estamos um pouco à espera que ele se junte a nós, porque o nosso Hugo está a ser bastante requisitado, digamos que somos paparazzi da astrofísica. Teve uma pequena conferência e fomos agora informados logo a seguir a esta, foi transmitida para os jornalistas, e como viram, só os jornalistas é que terão por questões, e qualquer momento ele poderá ligar-se então, e estamos aqui à espera dele para o recebermos e para pormos as nossas perguntas. E vocês também ponham as vossas na janela de chat do YouTube do nosso canal, que estaremos aqui disponíveis para colocar ao Hugo. Esperamos ter à mesma os 30 minutos que tínhamos combinado com ele e com os colegas do ALMA. A seguir temos às 3h30 a nossa sessão de Q&A, mas se conseguimos esticar um bocadinho o tempo que temos disponível com ele para aproveitar, porque acho que é uma oportunidade única, talvez não haja problema de começar um bocadinho mais tarde, então, a nossa ligação ao Q&A. Portanto, é que o público pode, através do Twitter, como viram no hashtag que está na nossa página do ESO, ou através também da janela de chat para as vossas questões. Agora sim, os cientistas, irão responder em tempo real às vossas questões. Mas, para já, esperamos então que o nosso Hugo se ligue. Entretanto, devem ter visto as imagens que passaram aqui em loop, são imagens, montagens das várias observações feitas pelo EHT, dos quais o ALMA também está incluído, como viram, para ver o centro da nossa galáxia, que agora temos a confirmação que temos um buraco negro supermassivo, Sagitários A, e ver também o centro da galáxia Messier 87, ambas bastante distantes, ambos bastante grandes. Há pouco falei dos 4 milhões, foram aqui recebidos também de milhões de massas solares da nossa galáxia, e a de Messier 87 tem qualquer coisa como 6,5 milhões de massas solares. É uma das perguntas que estou ansioso para colocar ao Hugo, será o que é que representa na prática, quais são as consequências de termos estes autênticos monstros, digamos assim, estes poços gravíticos imensos no centro de galáxias, que consequências é que tem, e outras várias, e esperamos também as vossas perguntas. Entretanto, podemos também referir que este projeto assenta essencialmente naquela ideia de interferometria que eu falei no início, portanto, uma rede de vários telescópios, radiotelescópios, e no caso do Atacama no milímetro, que operam em conjunto. Portanto, já temos uma cadeia deles ligados no Atacama, no deserto do Atacama, que, como disseram na conferência, talvez a região, talvez não, é de certeza, a região mais árida do planeta, e o facto de também estar a uma grande altitude também facilita as observações, como podem imaginar. Aliás, é um sítio ideal para fazer missões análogas de Marte ou Lua, porque até uma região lá que se chama paisagem lunar, porque tem um ambiente mais parecido com o do nosso satélite ou com o do planeta vermelho. E também temos outras cadeias de outras redes de telescópios, todos ligados também à linha, ground-based, como eles costumam dizer em astrofísica, noutras regiões do planeta. Portanto, e todas estas ligadas em conjunto têm tal efeito que é muito usado em astrofísica, esta técnica de obter como que um resultado como se fosse de um telescópio único, com um diâmetro imenso, e como o diâmetro de um telescópio é diretamente proporcional à sua capacidade de resolução de boa imagem com muito detalhe. E a possibilidade de juntar todos estes telescópios que observam individualmente o mesmo alvo, digamos assim, vem muito detalhe para a imagem final. Isto não faço ideia, mas serão se calhar gigas de imagens, portanto são imagens que podem ser estudadas durante anos e anos a fio, com muita coisa de novo para trazer para os nossos astrofísicos. E a mim pessoalmente tem um imenso gozo ver a satisfação, logo da primeira cientista que falou, que aquele famoso momento eureka, não é? Que têm os cientistas, de não só estar a partilhar uma descoberta importante para a humanidade, como fazê-la uma plateia em que está o mundo inteiro a assistir. E isso deve ser qualquer coisa de bastante recompensador. Portanto, agora aguardamos o Hugo. Temos aqui a informação que ele está a terminar a sua entrevista local, lá no Alma. E, entretanto, chama a atenção que nossa página do ESO, ESO.pt, podem encontrar vários recursos. Basta clicar mesmo, diz recursos, para usar em sala de aula. Agora falo claramente para os nossos professores e alunos que possam estar a assistir, eventualmente, de várias áreas transversais a este tema. Relativamente a buracos negros, vamos agora também investir mais, vamos aproveitar esta própria sessão e uma outra que vamos ter em junho para criar novos recursos também para usar em sala de aula. E já agora aproveito de falar já dessa, já que o Hugo também está ligeiramente atrasado. Dia 21 de junho vamos ter novamente o Hugo connosco, desta vez presencialmente, no pavilhão. Espero que estejam disponíveis para vir cá assistir e que nessa altura não haja problemas com a pandemia, que as pessoas possam vir livremente. E será uma sessão que não temos ainda hora marcada, mas umas horinhas ainda vamos estar a conversa com o Hugo e ele falar-nos-á basicamente tudo aquilo que souber sobre buracos negros, porque ou a titulação não fosse tudo o que sempre quis saber sobre buracos negros. Portanto, ele aceitou o desafio e, como tal, vamos tê-lo aqui connosco para falar abertamente sobre o assunto. E perceber também esta diferença entre buracos negros e buracos negros supermassivos, que é ao que parece todas as galáxias agora têm no seu interior. Não sei se, dado o relativo atraso do Hugo, se talvez, para aqui aos meus colegas, podemos passar um dos vídeos e eu agora explico o que é que viram há bocadinho e podem ver novamente agora. Tanto do... Ok, estamos já a ver um deles. Estamos a ver aqui junto à constelação da Virgem. Podemos observar então a galáxia MSI 87. Esta, claro que não é assim que a observamos a olho nu, tem que ser com um telescópio bastante potente. Aqui, diga-se de passagem, que temos a sobreposição de várias imagens. E então todas juntas criaram esta espécie de animação. Aqui vemos a galáxia em todo o seu esplendor. E lá no interior sabemos então da existência deste buraco negro cuja sombra, outra questão que também vamos colocar no nome, foi observada, foi fotografada. E bem lá no centro temos então aqui os vestígios da luz que, ao que parece, digo eu que sou um leigo neste assunto, apesar de ter estudado astrofísica, mas a astrofísica é uma área muito vaga, ao que parece tem corresponde àquilo que é previsto para a teoria da relatividade geral de Einstein. E agora estamos a ver já Sagitários 1 no centro da nossa própria Via Láctea, e creio que neste momento temos o Hugo connosco. Olá, Hugo. Olá, Hugo. Olá, prazer em ver-te. Tudo bem? Hoje ninguém te larga, não é? Os jornalistas em cima. Olha, antes de mais, muitos parabéns.
Muito obrigado.
Eu fiquei com aquela pele de galinha ao ver a notícia. Por acaso, não sei porque não passou pela cabeça que pudéssemos estar na presença da segunda fotografia da sombra, lá está, da sombra, de um buraco negro, que por acaso é o que está no centro da nossa galáxia. Ora, já há pouco falei aqui às pessoas, mas tu talvez queres te apresentar a ti próprio, aí com esse fundo fantástico por trás, no Atacama, no Chile, e perguntava-te se em algum momento, e pronto, podes falar de ti próprio, e já agora respondeste a minha questão, durante a primeira campanha de observação do EHT e algum momento em que tiveste vontade de gritar Eureka?
Sim, não, ou seja, o que se passou foi, primeiro, obrigado por me terem convidado para este evento.
Mas era nosso.
É bom estar a falar português, mostrar que podemos chegar aqui ao Chile e contribuir desta maneira para o conhecimento científico. Efetivamente, o momento Eureka foi com a M87 e eu costumo dizer isto, foi sabes aquele momento quando tu vês o resultado, relaxas na cadeira e dizes, fogo, chegamos. Conseguimos.
Muito bom.
Pá, mais porque havia todas estas incertezas. Quando foi para M87, não havia a certeza da massa do buraco negro supermassivo. Havia uma incerteza do fator 2. E um fator 2 era suficiente para não se ver nada. Efetivamente, por sorte, a estimativa da massa era maior e por isso conseguiu-se fazer aquela imagem. E quando eu a vi, foi mais perto do anúncio, foi mesmo aquele espetáculo. O facto de, não sei, talvez uma sensação de sentir-me útil para a sociedade. E neste caso para o conhecimento científico, que é um grande salto. É primeiro mostrar que conseguimos fazer. Estás a cimentar as bases para fazer outro tipo de observações, outro tipo de desenvolvimento. Neste caso, falou-se também o facto da possibilidade de enviar um telescópio para o espaço para apoiar este tipo de observações, em que o detalhe melhorará. As pessoas, se calhar, já não vão dizer esta é uma imagem completamente desfocada. Com muito mais detalhe. Vai haver, já este ano e o anterior, conseguimos observar com mais estações, portanto, a qualidade da imagem melhorará. E isto, de novo, isto é só ainda dados de 2017. E isto para ver, para que tenham um bocado a noção de... isto é o tempo que demora para, efetivamente, apresentar dados revolucionários, resultados revolucionários. Precisam ser testados até ao limite, precisam de efetivamente explorar todos os parâmetros de o que é que se consegue, com o que é que se consegue explicar estes dados, e é bem importante que as pessoas percebam que isto é algo... a ciência procura respostas, mas a resposta que vem tem sempre uma espécie de incerteza associada. E não há uma resposta perfeita. Quando houver, ficamos sem trabalho, mas eu digo que é de certa maneira impossível, porque não dá. E as pessoas temos que aceitar isso. Temos uma definição de o rumo onde vamos. E estas observações estão a mostrar que estamos no rumo correto, e precisamos de mais. Os astrónomos dizem sempre, precisamos de mais. Mas depois precisamos que alguém nos apoie.
Claramente. E isso ficou bem claro, que estão no rumo certo na conferência que nós tivemos a assistir. E presumo também que o Alma tenha sido um sucesso. E já agora, pronto, é sempre bom realçar que és o nosso grande embaixador português num momento histórico como este, em que finalmente temos uma imagem muito detalhada dentro da nossa galáxia. E agora não te resisto a fazer uma pergunta, talvez uma pequena maldade. Fala-se aqui muito isso respira fundo, aqui este pormenor que não fotografámos o buraco negro, mas sim a sombra. O que é afinal a sombra de um buraco negro?
É a ausência de luz. Se a pergunta é o que é a sombra?
Já posso reformular uma questão. Em que medida é que, não se podendo fotografar o buraco negro, consegue-se fotografar a sombra, o que parece estranho para nós leigos no assunto, em que a sombra também é escura, tal como o próprio buraco negro, não é?
Sim. A implicação de que não a vemos é um espetáculo, por exemplo. Porque mostra a nossa capacidade de fazer um puzzle sem todas as peças, fazer uma sopa sem todos os ingredientes. E o facto de estarmos a conseguir indiretamente perceber que este buraco negro está a rodar, na nossa perspectiva, estamos a vê-lo de cima, e ele está a rodar no sentido contrário ao ponteiro do relógio, Mas isto tudo, através do como se comporta o material que está à volta desse buraco negro, o mesmo aconteceu com a M87, é de certa maneira incrível, porque mostra que o caminho que já caminhámos até agora foi, de certa maneira, consistente, que nos possibilitou, efetivamente, fazer estes passos, esta descrição detalhada, com uma fotografia que pessoas dizem que não é detalhada o suficiente, mas que nos permitiu saber tanto, só com estas imagens, porque, novamente, houve vários dias de observação, é uma fonte que varia, a morfologia varia durante a observação, e isso foi uma grande dificuldade, e por isso é que só agora em 2022 é que se apresentam os resultados. Muitas coisas complicaram a situação para o Sagitários A comparativamente a M87. Mas, só para que se tenha uma noção, o detalhe que o EHT permite é como se alguém, ou eu, estou aqui, não através do Zoom, mas estou aqui no Chile com uma agulha na mão e alguém diretamente de Portugal tenta observar através do buraco da agulha. Está bem? Okay. E eu tenho aqui, por exemplo, aí ver se eu consigo, está aqui. E o tamanho da sombra do buraco negro é como se eu tivesse a segurar esta caneta assim, e vocês desde Portugal tentavam definir o buraco da caneta, este buraco, está a ver? Mas desde Portugal portanto,
não venham dizer que não é detalhada, porque
estamos
isto é
limitados
fantástico.
ao tamanho da Terra neste momento, e por isso é que se fala de enviar algo para o espaço, por exemplo.
Exatamente.
É uma das possibilidades.
Ok. Portanto, o James Webb poderá ter algum contributo, de alguma forma?
O James Webb não consegue este tipo de detalhe. A resolução do James Webb está na ordem, talvez, de... Sim, está mil vezes acima ou 1000 vezes pior do que o EHT permite. O que o James Webb vai conseguir é, efetivamente, estudar para muitos casos, por exemplo, o EHT, este tipo de observação, com este detalhe físico, só consegue para estas duas fontes. Depois, nas outras, consegue com a mesma precisão, mas não consegue resolver porque elas ou estão mais longe, ou são mais pequenas, blá blá.
Certo.
Mas é sempre um número limitado de fontes, enquanto que o James Webb irá fazer isto para milhões de galáxias, a ver? Buscar outros indicadores indiretos do comportamento de buracos negros supermassivos, e estatisticamente vai-nos dar, de certeza, respostas revolucionárias que nos permitirão estudar como se comportam e fisicamente como é que se comporta o gás nas imediações do buraco negro, e com isso também perceber efetivamente se o papel deles é relevante na evolução das galáxias, como hoje em dia é uma receita que os modelos de evolução de galáxia usam sempre, mas até agora as certezas ainda
Claro. Portanto, o James Webb é mais o todo, enquanto que o projeto EHT, com a presença do homem, é uma coisa mais para o individual, com resolução, já para não falar de interferometria que está por trás, não é? Que permite uma maior capacidade.
São técnicas diferentes, observam em partes do espectro diferentes, portanto, são complementares. Sim.
E já agora, então Einstein tem razão. A teoria da relatividade geral continua a ser confirmada para estas observações.
Sim. Ou seja, de certa maneira, não seria muito estranho que não o fizera, porque fomos a um buraco negro com uma massa de 1.000 milhão de massas solares e verificámos que sim. Depois as ondas gravitacionais mostraram que sim também para buracos negros estelares, portanto algumas dezenas de massas solares, e agora o Sagitários A está no meio deles, no meio destes dois cenários. E se alguma coisa falha, seria algo bem estranho. Se vocês forem no detalhe dos artigos, ainda há alguma coisa que... ainda há uns detalhes que ficam por explicar. Por exemplo, os modelos que se criaram para explicar o comportamento e as imagens, neste caso de Sagitários A, o que aconteceu foi que a variabilidade que nós vemos com o Balma, a variabilidade da luz durante as observações, não se consegue explicar bem com estes modelos. Portanto, há sempre alguma coisa ali que falha. Portanto, isso é algo que se irá tentar explicar no futuro. Pronto, mais trabalho para nós, o que é bom. Mas sim.
No seguimento que estavas a dizer, sim, no seguimento que estavas a dizer há pouco, isto tudo se conjuga, quer dizer, fazemos uma pergunta, a resposta poderá não ser satisfatória, mas surgem-nos mais perguntas, como tu dizes, mostram que estamos no caminho certo.
Exato.
Portanto, e é bom, realmente, não ficar sem trabalho, nunca ficarás, mas saber o que é que temos que fazer agora de futuro. Essa era uma pergunta que tinha para o fim, vou guardar para o fim. E agora, já que tu falaste nisso, dos buracos negros estelares, buracos negros supermassivos, qual é, na prática, o que é que significa nós dizermos que temos a nossa galáxia e muitas outras galáxias têm no seu interior um buraco negro supermassivo? Sim, estás a perceber tipo, as consequências, o que é que...
Sim, bem...
Desculpa interromper, eu só pergunto isto porque há muitas pessoas, e eu vejo isso nos vários eventos que temos aqui na Ciência Viva, e até jovens e professores, mas o buraco negro é uma coisa má, não é? Porque suga tudo que está à sua volta, e é um pouco, eu faço esta pergunta um pouco para desdramatizar essa ideia.
O buraco negro tem os buracos negros, especialmente os supermassivos, têm como que uma dicotomia. Ou seja, eles, de certa maneira, não se importam com o que passa no extremo da nossa galáxia, ou da galáxia em questão, mas podem afetá-la. Podem afetá-la de duas maneiras. A mais famosa é que, com a radiação que sai deste ambiente extremo que está à volta deles, a radiação que sai de lá é tão energética que aquece o gás da galáxia até um ponto que deixa de permitir que se formem estrelas. E assim a galáxia não cresce. Não é? Ou então perturba o gás de tal maneira que, novamente, não permite que estrelas se formem. Mas há cada vez mais evidência de alguns casos em que, efetivamente, pode criar estrelas, ou pode criar as condições para que se criem estrelas e, potencialmente, não sei, a vida. Pronto. O que se passa é que, quando há estes jatos que saem das imediações do buraco negro, eles são muito energéticos, vão muito colimados, mas depois, mais longe, como que abrem e já não são tão agressivos. E aí o que eles podem fazer é empurrar o gás e compactar o gás, permitindo que ele se coagule e forme estrelas. Por isso é que eu estou a falar desta dicotomia, ou seja, o segundo cenário não é um cenário que se observe tanto, mas, verdade seja dita, as evidências para o primeiro, há algumas, mas não é algo que afete, porque há outras evidências que mostram que talvez não afete a longo prazo o crescimento das galáxias. É, neste momento, uma receita, basicamente. O buraco negro é, em geral, tanto os estelares como os que estão nos centros galácticos, acho que faz parte daquele imaginário, ou talvez espanto humano, que é: eu não me quero aproximar, mas quero ver.
Ver aquilo que é invisível.
Isto é espetacular, eu sei que isto é espetacular e é algo que me ultrapassa completamente, mas não me quero aproximar, não me quero arriscar. E isso está bem, ou seja, claro, se uma pessoa se aproxima de lá, o seu futuro é um bocado
sim.
mau, mas depois há pessoas que dizem: pronto, há pessoas que se calhar arriscar-se-iam só para dizer eu estive lá. Pronto.
Está muito bem visto. É interessante o que acabaste de dizer, quer dizer, aquilo que é visto por muita gente como uma representação de morte, de finitude, de repente acaba por ser também ali onde pode nascer a vida. Já agora, para quem não sabe também, e tu corriges-me se estiver enganado, os tais jatos que eu estava aqui a falar, emitem na região do espectro do raios gama, do raio X, são as mais altas energias que existem no universo. Portanto, aquilo que supostamente absorve a energia toda, a luz toda, que é energia pura, também emite de alguma forma.
Estes jatos podem-se observar, se observam diretamente, podem estar a emitir em qualquer região do espectro eletromagnético. E é um espetáculo.
É mesmo. E Hugo, e tu? Já agora estamos aqui a falar contigo, o que é que a tua colaboração, a tua participação, tu operaste o Alma já na primeira campanha, o que é que fizeste? Conta-nos.
O meu papel foi sempre na parte de preparação das observações, executar as observações e depois calibrar os dados que saíram do ALMA. Brevemente é isto.
Ok.
Mas todo o trabalho por trás é perceber qual é o plano que vamos seguir. Porquê? Porque o EHT tem um modo operandi que é um bocado difícil, é muito dinâmico. Entre as 3 e as 5 da tarde do Chile, não é? Temos sempre que saber se vamos observar esse dia ou não. E isso depende das condições operativas, se cada estação está operacional, tanto de modo técnico como de modo de clima, tá bem? Meteorológico, e com isso depois sabemos se observamos ou não. Mas para isso nós temos de estar prontos para todas as noites, porque não sabemos qual é que vamos observar, qual é que deixamos de observar. Então temos que ter ali sempre plano A, plano B e às vezes plano C. Tá? Especialmente este de 2017 foi muito dinâmico, porque houve o Sagitário A foi observado por 5 dias e o Alma só participou em 3. E houve um grande esforço para pôr o Alma a observar a maior quantidade de vezes possível, mas estamos sempre limitados. Nós não podemos estar a chover e a nevar e estragar as antenas e deitar para o charco um projeto de 1.000 milhões. Pronto, essa parte da observação é bastante crítico. Talvez a adrenalina até sabe bem, mas é divertido perceber como é que depois como é que é o comportamento humano nestas condições, como é que o pessoal se organiza, e isso também vem desde meses anteriores, e neste caso anos anteriores à preparação do sistema do Alma. Depois, a parte de calibração dos dados era algo também completamente novo. Nós, ao mesmo tempo que estávamos a calibrar, estávamos a aprender como é que o sistema funcionava efetivamente, os diferentes detalhes que às vezes nos escapavam, e estávamos ali a corrigir no momento, calibrávamos e de novo às tantas, esquecemos desta parte, temos que fazer tudo outra vez. Portanto, isso foi anos bastante estressantes, mas aprendemos imenso. E a parte disto é que os dados que calibramos com o ALMA depois são muito importantes para a combinação do sinal que vem do ALMA com as outras 7 estações, neste caso em 2007 eram 8 em total. Portanto, eles também estavam dependentes do que é que nós lhes íamos enviar, porque o ALMA é efetivamente a estação-chave do EHT. E sem o ALMA não terias conseguido a qualidade de imagem que apresentámos hoje. Estejas contente com a qualidade da imagem ou não, isto é o melhor que conseguimos e conseguiu-se por causa do ALMA. Ou seja, não é sozinho, mas é aquela estação que fez a diferença total mesmo.
E aquilo que falaste há pouco, são observatórios em várias regiões do mundo, também não é por acaso, eu há pouco referi isso, espero não me ter enganado, que foi escolhido março e abril para fazer esta campanha 2 meses, porque a probabilidade de haver diferenças de temperatura muito bruscas é menor, não é? Que facilita também a qualidade das imagens.
Sim, ou seja, março, abril é sempre, não é o ideal, mas é também o melhor que conseguimos, porque vivemos num planeta que é um geóide, inclinado, tem estações do ano, portanto não se consegue observar sempre com todas as estações no verão, ou talvez até melhor é no inverno, noites frias, longas, e essas são as melhores, mas quando uma estação está no inverno, a outra está no verão, portanto isso faz com que nós tenhamos que organizar estas observações tanto em março e abril, e até há a possibilidade com o GMVA, que é outra rede de telescópios, de fazê-lo em setembro e outubro. Portanto, há sempre estas duas...
Primaveras e outonos, pois, exato.
Mas é isso, é depois toda essa dinâmica operacional que torna a coisa divertida mesmo.
Sem dúvida. Olha, eu não sei quanto tempo mais tens disponível, eu tinha aqui ainda mais uma ou duas perguntinhas.
Força.
É? Ok. Então uma era, portanto, já imagino há algum tempo para compararem com algum cuidado, portanto, as imagens que obtiveram do Sagitários A, como a do buraco negro da Messier 87. Alguma característica comum, interessante, digna de nota, ou mesmo diferenças que já tenham notado? Ou é muito cedo para fazer este tipo de afirmações?
Não, logo a pergunta que tu fazes é impressionante, e isso também tem a ver com estarmos num bom caminho, é o quão parecidos são. Não é só porque utilizamos a mesma cor para as imagens, é mesmo porque, efetivamente...
Eu até pensei que estavam a recuperar a imagem da outra observação.
Mas há esta semelhança de um anel que não é perfeito, que é assimétrico. Agora, as diferenças que já se esperavam é que o período de uma fonte é diferente da outra. O período da M87 é na ordem das semanas, meses, depende de parte é que estás a falar, enquanto que no Sagitário A estamos a falar de entre 8 minutos, meia hora, portanto, e nós observamos durante 8 horas cada vez, entre 4 e 8 horas, portanto, logo, tu conheces um bocado melhor, ou seja, tu quando estás a fazer este tipo de observações, logo o que tu assumes logo por base é que durante a tua observação a fonte morfologicamente não vai mudar, mas esta está sempre está sempre a mudar e dificulta muito a análise dos dados, e por isso é que demorou mais. É quase como, e isto tem a ver com, bem, levando ao limite, mesmo no horizonte de eventos, na borda do horizonte de eventos, tens a última órbita dos fotões. Portanto, é basicamente a luz a andar à volta do horizonte de eventos, também, e a luz tem velocidade finita, pelo menos quanto sabemos, e agora, imaginem o que é ter a mesma velocidade, e eu vou dar a volta à mesa, dou a volta à mesa muito mais rapidamente do que dou a volta ao quarteirão. É basicamente a mesma coisa.
Ok.
Portanto,
acho que estou a perceber. Mas agora falaste aí numa coisa e eu não vou deixar passar, que é o horizonte de eventos. Achas que é uma coisa simples de definir, só para as pessoas terem uma ideia?
Comecemos com o que é que significa ser um buraco negro. Eu estou cá na Terra e pego nesta maçã e tento atirar esta maçã para fora da Terra. Eu sei, e vocês sabem, que eu não sou assim tão forte. Portanto, eu para mandar esta maçã para fora, preciso de pôr num foguetão, ou logo que seja, e enviar para o espaço. O que é que esse foguetão implica? Ele vai atingir uma velocidade, que é a velocidade de escape, que permite sair da influência gravítica da Terra. Essa é a velocidade necessária. Agora, a velocidade necessária nestes buracos negros, os solares, é maior do que a da luz. E como se assume que não se consegue ultrapassar a velocidade da luz, nada sai de lá. E como os nossos telescópios, neste momento, detectam luz, e se ela não sai de lá, se ela não consegue escapar do horizonte de eventos, então não temos essa informação cá fora. Não quer dizer que a informação se tenha perdido lá dentro, mas não temos cá fora, não temos maneira de aceder. E o horizonte de eventos marca esse limite. É o limite a partir do qual tu, se não estás a correr mais veloz do que a luz, já não sais da influência gravítica daquele corpo. Agora, o que está lá dentro, aí não me perguntes, porque sei tanto quanto tu e como qualquer bebé que nasceu neste momento.
Exato. Até que uma vez lá dentro sofremos a famosa espaguetificação, não é? Que se diz.
Nem sempre.
Nem sempre.
Nem sempre. Porque isso acontece mais em buracos negros mais pequenos. Quando fores para buracos negros maiores, o teu tamanho em comparação ao corpo em si é tão diferente que os teus pés, a influência gravítica nos teus pés, basicamente é efeito maré, a influência gravítica diferencial entre os teus pés e a cabeça não é assim tão diferente, e já não, podes sentir um bocadinho esticadito, ficas mais alto.
Pronto, é o que acontece aos astronautas. Antes de voltarem para a Terra, claro. Olha, na conferência disseram, já perto do fim, mas o melhor ainda está para vir. Criaram ali um certo suspense. Já há pouco falaste um pouco nisso, mas o que é que segue, ou na tua opinião, o que é que espera o futuro, para além das tais perguntas novas que surgem, e o rumo está mais ou menos traçado, mas o que é que tu idealizas, o que é que tu esperas?
O que eu espero é que a comunidade científica perceba o que é que se consegue fazer com este tipo de observações e continua a pedir tempo para fazer este tipo de observações noutras fontes em que não se consegue resolver a sombra, mas consegue-se estudar os jatos, por exemplo, a formação de jatos, e com isso é bem importante. E há outras dezenas de fontes que já observamos desde 2017. Nós tivemos a campanha 2017, 2018, depois 2019 foi cancelada, mas depois de 2020 começou a pandemia, 2021 e 2022. Portanto, já temos 4 anos em que observamos já algumas, diria dezenas de fontes. Portanto, toda essa informação está a ser processada. Nos últimos 2 anos houve publicações que se calhar não tiveram esta atenção toda, mas que também nos deram mais um passo revolucionário na compreensão da formação dos jatos. E as imagens são incríveis, o detalhe com que conseguimos fazer e o facto de que estes monstros, nós conseguimos ver estes monstros a mexer. Com uma cadência de, às vezes, nem dias. E o facto de os ver a mexer, que há movimento, que não é assim tipo uma fotografia estática, é incrível e, não sei, não é um momento de eureka, mas é um daqueles momentos de encostas na cadeira e aprecias.
Quanto mais não seja, suponho eu, pelo menos no mundo das artes, ver tantos filmes de ficção científica, cada vez a falar mais de buracos negros, são coisas muito cativantes, até aos meninos desde novos que nos perguntam isso nas ações, com mais jovens, a gente não sabe bem do que é que há de responder. Daí espero que haja mais interesse de parte de quem manda para investir mais nestas áreas, para saber, ter mais conhecimento, não é?
Sim, porque depois é também com estas atividades de tentar explicar o que é que nós fazemos ao público em geral, também mostrar a importância, a relevância de fazer este tipo de estudos e entusiasmar mais pessoas a meterem-se pela área da ciência. Não é preciso que seja da astronomia, há várias áreas na ciência e a curiosidade está sempre lá. Acho que a palavra-chave aqui é a curiosidade. E não há como escapar. A partir do momento em que descobres o sabor da descoberta, acho que começa a ser começa a ser, não sei como é, viciante às vezes.
Sim.
E é uma coisa boa, é dos bons vícios.
É sim, senhor. Eu quando comecei na astrofísica e aquele meu breve período na investigação, o que me fascinava era a matemática como a linguagem do universo, que está tão presente nesta área. As equações de Einstein, os tensores, tudo por aí fora. Mas depois a seguir, é como estavas a dizer agora, a parte mais humana, que é que está por trás disto tudo, é aqui muitas outras áreas transversais.
Sim, se vais a ver, o humano quando nasce sente-se perdido, tipo, onde é que eu estou? Que é isto? Às vezes olhas começaste por olhar para o teu pai, para a tua mãe, e quem é que são estas pessoas? Não é? É tipo, a tua mãe está-te a dar leite e tu gostas, pá, isto é bom. Pronto. É isto. E começas logo, tu intrinsecamente nasces um cientista. E, portanto, acho que a sociedade devia explorar mais este facto. E não está a explorar tanto. E às vezes limita até. Portanto, é bom que haja estes centros tipo Ciência Viva e todos os programas que vocês têm são bem importantes para cativar e continuar com motivar esse instinto e que não se perca. Porque depois também é importantíssimo para a tua própria vida. Que tu questiones, que às vezes não é que sejas um refilão e que sempre que te dizem não é assim, tu dizes não, é porque eu não concordo. Não, falem, há que falar, há que discutir, há que questionar, mas questionar com raciocínio. E esse raciocínio também se trabalha. E trabalha-se desde que nasceste. Tá bem? Depois treina-se. Depois é tudo treino. Não há área nenhuma, seja ciência ou não, que não requeira treino. Portanto, acho que
é como dizes, desde já agradeço as tuas palavras, é essa a nossa missão, esperamos cumprir, mas as crianças, já quando nascem, aquele prazer de descoberta, né? Olham para o mundo à sua volta com os olhos a brilhar, é um pouco que eu vejo também nos teus olhos e de todos os cientistas que falaram hoje, porque no fundo, e isto foi-me dito recentemente por um neurologista, ao que parece uma conversa interessante por acaso, que o que mais faz desenvolver os nossos neurónios é o conhecimento e a satisfação dessa sede de conhecimento. E contribui também para a nossa felicidade, e é uma ótima razão para contribuir para estas descobertas fantásticas. Olha, Hugo, muito obrigado, não te quero tomar mais tempo, deve estar cansadíssimo. E recordo aqui toda a gente e que contaremos no dia 21 de junho contigo, desta vez presencialmente. Marquem já na agenda. A sessão vai se chamar Tudo o que quis saber sobre buracos negros. O Hugo aceitou o nosso desafio. Eu estava a pensar.
Já vos posso dizer que vou falhar completamente nesse desafio.
Não, mas todos nós estamos a falhar e a aprender e estas novas perguntas que surgem. Portanto, sim, realmente cria expectativas, mas nós sabemos que temos que contar contigo e também terá aqui a professora Ana Noronha, diretora executiva do pavilhão, e vai ser muito interessante, exatamente. E teremos também a arranjar algumas atividades, eventualmente, para fazer em sala de aula. Pronto, e é isto. Vou-te libertar, que deves estar a precisar. Não sei que horas estão aí.
São 11.
11 da manhã, pois, uma manhã logo com muita coisa a partilhar para o mundo inteiro, fantástico.
Começou a ser.
Bom, olha, obrigado mais uma vez e vemos
em breve.
Muito
obrigado a vocês, até breve. Deus.
Grande abraço, tchau. E pronto, e cá tivemos o nosso Hugo, teve a simpatia e a disponibilidade de ter aqui mais tempo connosco, e agora vou então pedir aos nossos colegas para passarem a emissão para o Q&A, as perguntas e respostas, às quais vocês, público, podem participar através do chat ou através do hashtag do Twitter. E vemos novamente no final da sessão. Tá? Obrigado e até já.
Well, so the point is actually even if Sagittarius A star were launching very small jets, and we think there's a pretty good chance, I mean, at least the models that we use predict there should be jets, but we have to remember that Sagittarius star is basically something like tens of or 100,000 times less powerful than M87. So if you just turn the crank down, its ability to make powerful jets is hampered. And then you have this complicated mess in the galactic center, and trying to pick out some weak feature, we already have known for a while that it would be quite difficult to see. So the question is whether when we have our upcoming data sets from the coming years, when we have more telescopes, and we also fill in some of the baselines, will we be able to maybe connect this, fuzzy sort of donut thing to maybe some kind of extended emission? It's the same issue we'd like to do with M87. The question about the mass is, about the galaxy, we're on such tiny scales that we wouldn't be able to get a new constraint. But I would say in terms of constraining the mass, we do constrain the mass in our publication. It's just that we don't do as good a job as has already been done by the Nobel Prize winners of Andrea Ghez and Reinhard Genzel's groups.
I guess you could say that in a way, like the orbits of stars around the black hole provide you like a more direct, a more straightforward way of getting the mass rather than the kind of modeling you have to do with this data, right?
Yeah, I mean, Kepler's laws are pretty easy, in some sense, exactly. They have extremely, precise data. So.
Even though we mentioned briefly the mass of the galaxy, which, as you say, you cannot constrain because the scales are very different, I wanted to take this opportunity to also tackle another popular myth that goes around sometimes, which is the idea that because supermassive black holes are at the centers of galaxies, that they are somehow responsible for the galaxies spinning around them. So I wanted any of you to briefly explain why this is actually not the case. Like, what would happen if you remove the supermassive black hole in the Milky Way, for instance? Would the rest of the galaxy notice? I don't know. Whoever wants to take this question. Otherwise, I will assign any of you. No. So, Violeta.
The short answer is, if you were to remove it now, probably nothing. That's what would happen. The question is what role it had in the formation of our galaxy, and that in the fact that it looks like it does now. But the sphere of influence of the black hole itself on its surrounding is not very large. It's very small. So if you remove that, it wouldn't impact us directly. But maybe the evolution would change again. So I don't know if somebody wants to elaborate on this, or has different. Is more worried than I am.
Maybe a more indirect effect. I mean, the jets have been mentioned before, right? Sarah liked them very much in Sagittarius star. Unfortunately, we haven't seen that yet, but we see it in other galaxies, right? In M87, there's a very, very clear indication of a jet. Another galaxy, for example, is Centaurus A, where we also imaged a jet. And when these jets, when they plow through the galaxy, they actually impact the gas that is in the galaxy itself. It may be compressed, it may be heated, and that might trigger or actually hamper. It's a relatively active field of research, trigger or hamper star formation. So you may actually have the influence from the jet or other outflows from the central black hole. It's not only accreting, it's also putting stuff out there, and that might influence the whole evolution of the galaxy.
Okay. So we have a question from. Sorry, go ahead.
Yuri wanted to.
Sorry, I didn't see you. Sorry.
No, it's okay. I just wanted to quickly add to that about the jet stuff because I think it's really interesting. That we see evidence of a very violent past for Sagittarius A star for our galaxy. We have these things called Fermi Bubbles, which are these enormous radio lobe-like structures which extend above and below the plane of our galaxy. So they speak to some very violent, almost cataclysmic event that happened a very long time ago. And it's curious that we're in a period right now where everything's very quiet. And probably in some way a jet of some description or some enormous eruptive event is responsible for that. And so I think, what's really cool about these observations is we don't see a large-scale jet, as Sarah and Michael have said, but the question really is, why don't we see one? And yet, in the past, we seem to have indications there may have been something like that. I think it's really cool that we're having this rare opportunity now to finally have a look at the very heart and maybe start to answer these questions in time.
Yeah, actually, sorry, just a thought that occurred in my mind, and I wondered what would happen if Sage Star had a jet like M87, right? What would that mean for us? Maybe not good things.
Luckily, it's pretty far away, so.
Yeah, we should be safer, right?
And it's not in the center of our galaxy.
Yeah, exactly. I have a question for Violeta. So from Daniel Tapia. Someone mentioned in the American live stream that there are plans to observe the Sol Sagittarius A at different wavelengths to be able to detect more features. So he wants to know, first of all, what wavelengths these are, and also would you be able to resolve the black hole shadow with these as well?
Yeah. So yes, the EHT has been very active since these observations, and it will be further active. It's more planned ahead. Some observations have been taken. So these are 2017 observations, and observations have carried out the following years just to look back before looking into the future. We have observed in 2018, so the year after. There was a gap between 2019 and 20, also due to the pandemic and other constraints. And then 21 last year, and this year, 2020, a month ago, there were more observations. But there's more to come. So more observatories have joined. So it's not just more new wavelengths, more observatories have joined, and notably offering new baselines and covering the UV plane. That virtual telescope of the size of the Earth is getting filled up more nicely, and you can find more structure, also more larger scale structure, as Sarah was pointing out before. But yeah, going back to the future, so what is planned for 2023 is really exciting for DHD, and also exciting for those of us who worked towards it in the past, is the addition of a new frequency, a new band, which is higher frequency. We call it band 7 in jargon, so it's even higher frequency than what we're showing in this image. And it will allow to see potentially even closer to the black hole, because at high frequency, the resolution is improved as well.
Right.
So it is extremely exciting. And so that's to come in 2023, that's next year.
So let's stay on this topic, because we have a question from Sam on YouTube. So he's 14 years old, but very interested in astronomy. So he wants to know what is the next stage with the EHT. So I don't know if maybe Rocco or Roman want to elaborate a bit more on this.
Sure, I can take it. So I like to stress that this image we present today, which is in the background of Sarah, actually this is an image of a single day of a single year, 2017. So we have more days on the same year, and then we have additional observations in the following years, 2018, 2020, 2021, 2022, as Violeta also mentioned, which means we will be able to track the structural changes and time evolution of the source. And except from, it's not only Sagittarius A star and M87, we also have other targets, as Michael mentioned earlier, like Centaurus A, and then we have another binary black hole system candidate, which is OJ27. And besides this, we have more targets, and we also polarized light emission that we observed, so we can study the magnetic fields. So we have so many science cases to address in the next year. So the best maybe is yet to come. I don't know. I hope so. So Roman, if you want to add anything else here.
Yeah, absolutely. Yeah, there's a lot of science cases, and they tend to grow, the number of science cases with the better the observatory gets. Adding stations in particular is such a useful thing. It enhances our sensitivity in the image. We allow ourselves to be more sensitive to the low brightness features, for example, and taking more data reduces effectively the time over which we can generate an image. It's like exposure time, basically, if you think of photography. And so, yeah, that will hold tremendous promise in moving forward, and allows us to ask different types of questions in the future.
Can I also add something to that?
Yeah, absolutely, yes.
Because really, like for the very far future, really the holy grail for us has always been to go to even longer baselines. Right now, kind of limited by the size of the Earth. We have our telescope around the globe, and that size of the Earth determines our resolving power, right? That we can see these black holes. But there are also plans, as I said, far future ideas to launch satellites, like to launch really satellites with telescopes on them in an orbit around the Earth, like something like Chandra Observatory or the Hubble Space Telescopes. And we could then use these telescopes as an extension to our network. And with that, we would get an even higher resolution and we'll be able to take more pictures of even more black holes. So that could really blow up this whole field of research. So for someone, I think the question was asked by someone who's 14 years old. So for someone who is like an aspiring astronomer and who's now 14 years old, like for their career, that might be like a real possibility.
That's fantastic. Actually, I wanted to ask, I don't know, any of you, if someone wants to, if we have like more of these young future astronomers, what is the path that you think they should take if they want to pursue this as a career? It's a tricky question because, of course, there's not a single path. But I don't know if any of you wants to explain very briefly how they should go about doing this if they want to do this for a living. This is for anyone. I don't know.
Maybe I could say something because I didn't take a very typical path, so it's maybe
perfect.
In the US, we don't have to focus our studies until we get to university. And I actually was doing more arts. I was thinking I was going to go to art school. And, I was just interested in science and physics from reading a lot of science fiction and, comics and all that kind of stuff. And basically, I just started studying it in university and really liking physics. And then it was just curiosity driven from that point forward. So honestly, I never set out to do this and I never thought I would succeed in doing it. And I think that if I can do it, anyone can do it. So I think it's a really great thing to just be curiosity driven and try to just study what you find interesting.
Yeah, that's right.
Yeah. Can I add just a thing? I really like Sarah said, science fiction, because I was going to suggest to read science fiction as one of the paths. I think that really gets your mind sort of broadened a little bit, what you think is possible and what is not. And also, once you get to a bit older, maybe university stage, don't be shy of approaching people who you think do cool work, and create those connections early on, because maybe there is stuff for you to do there already, as a student. Yeah.
Yeah, I think if you talk to any random astronomer, the chances of them having followed a completely different path are really high. So I guess that's also a really good advice. Don't try to obsess perhaps with following a predefined path because you never know where you're going to end. I have a couple of questions for Siri. So we have several people, for instance, on YouTube, we have the RSC Planetarium in Calicut, asking about, now that we have the first image of Sagittarius A star, how much does this image conform with the expectations of the different models and simulations? And we also have someone else asking, are we learning something new about gravity or general relativity with this new image?
Right, so that's quite a lot to unpack there. I'll do my best to be brief. So in terms of the models and the simulations, so in the end we ended up calculating, I think, around 1.8 million images at a few different wavelengths of what the state of the matter around Sagittarius A star would look like at any given time. And we had a lot of constraints to play with this time. So we didn't just have the 1.3 millimeter or 230 gigahertz constraints. We had constraints at a few other wavelengths, including the infrared. We had variability constraints at very high energies. We have constraints also on the source size and asymmetry and so on. So we had a lot more constraints to play with. And when we applied all of those constraints to the many models that we created, it turned out that many of them didn't make the cut, and only a few survived. And those models which survived, they have a few common properties. And one of the first is that they tend to be in what we call a magnetically arrested state. So they're extremely magnetized. So they have a very high magnetic flux and have a very thin current sheet near the event horizon. And they're just very dominated by magnetic field. We also found that the models that we're creating favor an inclination angle which is closer to face on, which was surprising. And we also found that most of our models favored a distribution of radiating electrons, which basically necessitated the presence of a jet, which is something we don't actually see, but like the base of one. So a lot of those electrons were pushed outside of the plane and further away. And that's quite interesting too. And so it's actually quite a surprise that a lot of models were ruled out. Now, in terms of the other question, which is about general relativity and what do we learn? Well, we learn that, if I may say in British slang, Einstein did a bloody good job. And it turns out that The theory is remarkably consistent. I want to emphasize that this is the second time we've imaged a black hole. And of course, this is special because this is our own supermassive black hole. But there's a difference in mass here of over 1,500, factor of 1,500. And yet you see morphologically the structure of this ring is basically, it's consistent across these extremely different mass scales, which speaks to the macroscopic properties of black holes and the fact that this is a regime where gravity dominates. And just to give you a sense of how well, my final comment on how this speaks to validity and robustness of general relativity. So I've got a number that I like to quote, which is, so we find the ring diameter in these measurements. If you convert it to kilometers, it's about 63 million plus or minus 2.8. Now, if the black hole isn't spinning at all, so it's as large as it can possibly be, you get a number which is of the order of about 64. So it's right in the smack bang in the middle of what we find. And we don't take this image and just put a ring on it. We actually work with the interferometric data and we find a ring in that data. It's a Fourier transform of one. So we don't literally fit, there we go. We don't fit a ring to that. We actually look at the visibility data. But the point is we find something remarkably consistent with general relativity. I think that's just amazing.
Yeah. Yeah, it's incredible that, that the theory gets so many things right down to that level of accuracy, right?
Yeah, indeed.
All right, so we're having quite a lot of trouble scanning through the questions because we have so many of them. So we really, really appreciate the interest that you are showing. I have a question for Sarah by user Spider-Shan. They are asking which targets are being considered by the EHT for future observations?
Well, I think this sort of touches a bit on what Michael was talking about. Sorry. There's Michael Johnson and Michel Janssen in our collaboration. We're always doing this. But, at the moment, right, we're limited by the size of our planet. So in terms of the ones that we can actually see the ring, it's just these two, M87 and Sede star. But we actually have quite a lot of other black holes where we can see the inner parts of these jets. And for all these reasons, we've been talking about the fact that these jets can actually alter, the entire evolution of their galaxy, as well as, accelerate the highest energy particles. We're really interested in these. So we have targets we've already published, 3C279, Sen-A. There's many more in the pipeline. And then the thing that's going to be very interesting is when we start to move into this, space, because I think there we open ourselves up to an entire population. And so that's going to be, the long-term future. And the intermediate future will be what we call sort of the NG-EHT expansion, when we start to put baselines on the Earth that won't get us more horizon targets, but will get us many more of these supermassive black holes and jets. And I think that's going to be very interesting because, when we try to assess this whole population of these black holes throughout the universe, they're in all different shapes and sizes and all different types of powers. And we need to have a full population to be able to fully understand them, their evolution, their relationship to their galaxies. We need to understand this in multi-wavelength. And so you can imagine there'll be many, many years of observations as the telescope expands outwards in size and scope, together with multi-wavelengths.
I see. We talked before about whether we are safe or not from the black hole. We have a pretty interesting question here. I guess this could be for anyone. It's by user, I hope I pronounce this correctly, Chassis Earth Project. They're asking that since we are positioned face on to where the jets are supposed to be, what would happen if they should turn on or start firing up? Would we be in danger if we are looking directly at any possible jet that could come out? Any of you? I don't know.
We sort of talked about it before, right? I mean, Ziri was mentioning that there was a lot of activity in the past. I think we're pretty far away. So even if the jets did become more active, we're sitting right next to a pretty dangerous source as well, which is the sun, and it's bombarding us constantly with the same kinds of particles that the black hole is basically emitting. And so as long as it stays far away, our Earth's magnetic field, thankfully, is keeping us pretty safe from these types of particles. But you can imagine that if we were on a planet much closer to the jets, in fact, they could be quite catastrophic for life. Yes, so it's an interesting question, and maybe some unlucky aliens out there have to worry about this.
Okay, let's see. Yeah, sorry, apologies, 1 second. There we go. So this is a question, I guess, for everyone, but maybe Sarah, I guess. We have a user, Saida NEHC, on Twitter asking that since we observed the Sagittarius A star and we took pictures of it, what other features are still unknown? Other than the rotation direction of the black hole or the jets that can be seen right now, what is other stuff that could be crucial about the black hole, but we don't know yet? Anything that you could potentially discover that you haven't found yet?
I'm sure all of us have answers to this. I have one I could just start with, and that comes down to this flaring, actually, and the relationship to the activity and the feedback that this black hole can, impose and damage and sort of shake up its environment. There seems to maybe be a connection between this, because Sagittarius star is the absolutely weakest in terms of how much material it's eating and how bright it is. It's the weakest black hole that we can currently observe, so it's very, very dormant. And yet it seems to have these very interesting flickering flares that we don't see in other black holes. Other black holes, pretty much all supermassive black holes and stellar mass black holes that are, sort of eating but not eating a lot. So we call them sort of weakly accreting black holes, but they have jets fit on a very tight plane. They basically have a very tight relationship between the energy coming in, the energy going out, and their black hole masses. Sagittarius star is the only one that we know of that doesn't fit on this. And it's very interesting to think that maybe it has to do with the fact that these jets aren't there, or the jets aren't being somehow lit up by particles. So for me, that's a really pie in the sky kind of interesting question that hopefully we'll be able to learn more about in the coming years.
Does anyone else want to add anything?
Yeah, I guess one more thing about the detectable features in the future. It's really striking that there's a whole hierarchy of things that we can observe here. And it starts with what we call astrophysics sometimes, what the gas is doing around. That's usually the thing we're very sensitive to. But then we're trying to dig into other features about gravity, and that has to do with the ring and its persistence. And hopefully it doesn't depend on the wavelengths that we already discussed in the previous questions, and so on. And all these questions we can answer better and better just by keeping monitoring and looking at these sources for a longer time.
That's it. Well, unfortunately, we are running out of time because we should finish at 5:30. But I don't want to leave without getting your last impressions of this image. So I would like to go to do like a round and ask you to describe this image with like one word. Like if you had to use one single word to describe this image, what would it be? So let's start with I don't know, Roman.
I would say it's a ring. It's a little bit more than one word, I'm sorry. But
that's okay. One ring to rule them all, I guess. How about you, Violetta?
This is a really tough exercise because I can only think of sentences like Robert. I think I would say it's inspiring, also humanly inspiring because of the work of all the people behind.
I see. How about you, Rocco?
So I would say the universe is full of donuts. So
that's always good news, I guess, right?
Yeah, Homer will be happy.
How about you, Michal?
Well, yeah, I mean, Violetta already said inspiring, so I was trying to think of something else. I would say maybe rewarding for all of the work that has gone in trying to produce this amazing result.
How about you, Siri?
Tough question. I'd probably say magnificent. Magnificent that we're finally, as a civilization, able to see the heart of our own galaxy.
I completely agree, yeah. And finally, Sarah, how about you?
Oh, me? I'm sorry.
Yeah.
I mean, everyone said it. I still think we live in such an amazing time that billions of people have lived before us, and yet we're the ones that are currently on this planet that can see this. And I think, other people pointed this out, but other aliens elsewhere in the galaxy will look and see the same thing. So it's something really universal. It's the galaxy. It's our black hole, and it's just familiar and amazing.
Mm-hmm. Well, unfortunately, we are running out of time, so I want to thank all of you again for having joined us this afternoon to explain to the audience everything behind this magnificent, unique, historic, however you want to call it, image that we saw today. I'm sure that everyone online appreciate you giving some of your time to share your expertise and your contributions to this story. So once again, Sarah Markov, Michal Jansen, Roman Gold, Violetin Pellizzeri, Rocco Lico, and Ziri Junsi, thank you so much for being with us.
Thanks for you.
And,
Thanks for having us.
Thank you. Thank you.
Bye-bye. Thank you.
And to everyone else who has been following us, we hope that you have enjoyed the press conference and this live Q&A event. You will be able to listen to everything in a recording in case you missed some part of the event. Don't worry, everything has been recorded and you will be able to listen to it afterwards. And thanks again. We hope that you have.
Olá a todos novamente e pronto, foi a nossa sessão de Q&A, da ESO. Espero que tenham ainda podido aproveitar um pouco. Mais uma vez, desculpa que não acompanhámos desde o início, mas fazíamos questão de entrevistar o nosso Hugo Messias, que depois da sessão dele da Conferência de Imprensa também teve uma sessão à parte a seguir. E pronto, posto isto, resta-me lembrar-vos que no dia 21 de junho teremos uma sessão, agora presencial, à mesma com o Hugo Messias, a falar tudo o que sempre quiseram saber sobre buracos negros. E fiquem agora com esta boa notícia, que nós já temos fotografias também da sombra do buraco negro da nossa própria galáxia, não é só da M87. E em breve, na nossa página, daremos mais novidades sobre o evento dia 21. Obrigado a todos pela vossa presença, pela vossa participação e não se esqueçam de visitar o ESO.pt e a ciência vive. Tchau, obrigado a todos. Boa tarde.